All right, let's go ahead and get started here. So a week from today, we've got our first exam of the semester. And that's going to be covering everything through class 11. So today's class will be included. Tuesday's class will be included. Basically, chapters 2 and 3 from the textbook. You'll have 75 minutes to complete the exam. I've already posted the equation sheet that'll be available to you. And also there's that sample test that's there. So today we're going to continue talking about hydrostatic forces on curved surfaces and then a related subject, which is buoyancy. Any questions before we get into this hydrostatic force stuff? All right, well, just as a refresher, what's the two forces? When we did the hydrostatic forces on a curved surface, we broke it up into two parts in our last class. There's the horizontal force and the vertical force. So horizontal and vertical. How would you summarize what's the process for finding the magnitude of each of those forces? If we have some sort of a shape that's underneath the water surface, let's say that we have a curved gate of some sort that's holding water back, so it's underneath the water surface, and maybe we have a gate that is spherical in nature. We want to find out what are the horizontal and vertical forces. So what do the horizontal forces depend on? Okay, depends on the depth, yeah. There was an idea of projection that we talked about. So how would you work the word projection into explaining how you calculate the magnitude of the force? So force magnitude is what for the horizontal forces?
The vertical projection.
Okay, good. So we have to, for this curved shape, we have to prepare a vertical projection. So if it was a hemisphere, then the vertical projection would look like a circle. So we think about what does it look like, what does this curved shape look like when you're just viewing it from one direction? Okay, so the force magnitude is dependent on the vertical projection of the curved surface. So once we come up with what does that vertical projection look like, then we go through the same process that we did for flat surfaces. So we ask questions like, what is the depth of the centroid delta H? What is the orientation of that? Well, it's a vertical projection, so luckily our delta H is going to be equal to y bar. So that makes it easier for us to calculate the location of the force. So force location will be at ycp, which of course we know is y bar plus I divided by y bar A. So basically, the horizontal forces, that approach is the same as when we were doing forces on flat surfaces. Now what about the vertical forces? How do we, like if you were going to just very briefly, like in one sentence, explain the force magnitude is dependent on what? Force magnitude is dependent on All right. Yeah, we could maybe try and find the centroid, but the tricky part is on a shape like this, you don't necessarily know the center of volume quite as easily as we do when it is the horizontal forces. And so I think the alternate approach, because of that, is to look at the weight of the water above the surface. So the force magnitude is dependent on the weight of the water above the shape. Okay, now the location of the forces, the location of the vertical forces, that's where we go into that weighted average, where we're trying to break up that shape into components, and for each of the components find where is the location of that, and then coming up with a weighted average. But that's just meant to be kind of a review of what we did last time. So here's that very case. Here we have, well, no, this is a little bit different. When I was drawing on the whiteboard, I was drawing a hemisphere. This is not a hemisphere. This is just a curved gate. And so it was a flat surface that was curved into being a gate like this. Okay, so what we're given is 2 meters is the radius of curvature. It's 4 meters wide, so that would be this parameter. If we're having a curved gate, 4 meters is this distance. And we're going to do this handout problem. Let me give you a copy of it, just to kind of emphasize these steps. Now, on this one, I'm going to ask you to find the magnitude and the location of the horizontal forces, but only the magnitude of the vertical. We won't go through the entirety of finding the location of the vertical forces just for sake of time. Of course, you're free to collaborate and work on this one with your classmates together. So the magnitude of the horizontal force, the location of the horizontal force, and the magnitude of the vertical force. Note that this is not water. The liquid is not water. Okay, so I apologize that looks like my notes didn't scan in very clear for this one. So it's on the whiteboard though. If we want to calculate the horizontal forces, we have to find the depth of the centroid, so that's 4.7 meters. Then multiply that by the unit weight of this fluid. Since this fluid isn't water, we have to convert from this given density of 0.745 kilograms per liter. So if we multiply that by 1,000, that'll tell us how many kilograms per cubic meter, because there's 1,000 liters in a cubic meter. And then we multiply that by G to convert from density to the unit weight. So it's 7,308 newtons per meter cubed. So multiply the depth of the centroid, delta H, by the unit weight, multiplied by the area of the vertical projection. So the projection of that curved surface is a rectangle that has a height of 2 meters and a width of 4 meters. That's the dimension that's given in the problem statement that we don't see, that it's 4 meters wide gate. So the area of the projection is 8 square meters. And we still have to keep the projection in mind when we're calculating the area moment of inertia. We calculate the area moment of inertia for the vertical projection. So meaning that it has a width of 4 meters and a height of 2. So that when we're calculating the I of 2.667, we can substitute that into the YCP formula. So the hydrostatic horizontal force is located at a depth of 4.771 meters. Did anybody else get that same thing? Okay, good. Now the vertical forces, man, I really need to come up with some sort of a 3D tool so that we can start looking at these shapes from different angles. I was just briefly now trying to see if there was some shapes that were built right into PowerPoint that allow me to do that, but there isn't really. What I need is a three-dimensional cylinder view from the end. It only has cylinder views from the side. So anyways, there's essentially what we're doing is calculating the weight of the water. And as you can see on the whiteboard here, I've broken it up into 2 different spots. I've broken it into the weight of the water that's above the gate in this rectangular section, and then the weight of the water that's above the gate in this little wedge-shaped section, which is essentially a rectangle minus a quarter circle. And then once we find the net area, we can multiply it by the given width of 4 meters. So the volume of that section, the combined volume of the small piece and the larger piece, that's the rectangular shape. The larger piece is 29.6 cubic meters. The smaller piece is 3.434 cubic meters. So the combined volume multiplied by the unit weight, and then it'll tell you that the vertical forces are 241 kilonewtons. So that's the weight of the water above the gate. So hopefully that was useful practice just to re-emphasize the principles and the procedure that you use to solve these curved surface type problems. Let's turn our attention now to buoyancy, unless there are any questions on this handout. All right. Got a picture here. Let's try and do some detective work. What are we looking at? Okay. Yeah, so fuel. I heard somebody say fuel. That's a gas station, Sunoco. I think actually this picture, it's been a while since I got it, but I think it was from Charleston. So this is from the local area. What's that? It's a tank. Looks like a tank, and it came up out of the ground. Do you think somebody crawled down there and pushed it up? That's not it. Yeah. What pushed it up?
Water in the ground.
Exactly. Yeah. There's water in the ground. Now, this gas station, it's not in service. It's kind of an old gas station. You see these occasionally. Where's there one? Oh, the 7-Eleven, right? Right across from campus. That's out of service too, right? Oh, is it torn down? Man, shows how observant I am. I drive past it just once a day, that's all. All right, so here's the thing. When the gas station is closed, there's no more fuel in that tank. When there was fuel in the tank, then it was pretty heavy, and the weight of it acting downward was enough to keep it from submerging. But when you take all of the fuel out, suddenly now there's a big buoyant force. So that if the water table gets pretty high, let's say it's been wet weather, and the water table is high because the voids in the soil grains begin to fill up with water, now those hydrostatic forces are pushing upward on the tank. And in this case, the weight of the tank, the weight of the soil, and even the weight of the concrete acting downward, all of those forces were less than the buoyant force pushing up on the tank. So this is an illustration, kind of an unusual buoyant force application, but it's one that happened, and it's not alone. Actually, there are other spots where buoyant forces cause these empty storage tanks to come up out of the ground. Let's watch another illustration of buoyancy. This is of a submarine as it emerges from the water. So why was the submarine going from submerged to emerging from the water? Do you know what's happening on board that submarine that causes it to do that? Internal pressure? That's right. Yeah, so a submarine is essentially a hollow tube, and if it was completely hollow all the time, they wouldn't be able to get it underwater. So in its simplest form, we can just think of it as like a cylinder that's under the water. And so if it's totally empty, it's going to have a tendency to rise. And so what they do is they have these tanks that they can selectively empty and fill to change the net density of the submarine. In other words, they can change how much the submarine weighs so that they can adjust whether it's diving or whether it is submerging. And so here, it was submerging because they pumped air into those tanks, and so the water went outside of the submarine, and suddenly the submarine weighs less, and so it goes upward. Let's continue to watch the last part of the video. Why did it stop? How come it didn't keep going up even more? It reached equilibrium, right. So there came a point in which the buoyant forces that are pushing up on the submarine, F sub B, came into equilibrium with the weight of the submarine. So before, when it was submerged, they filled those tanks and it was in buoyant equilibrium. But then when they empty them, there comes a point where it comes back into equilibrium. And so what it was is that the buoyant forces only depend on the part of the submarine that's actually submerged, not on the entire volume of the submarine. That's why it doesn't just keep floating up out of the air and into outer space, is it comes into an equilibrium at the surface. And so like a barge, when you look at a barge going up and down the Ohio River, sometimes those barges sit pretty high in the river, and you think, wow, that's really a tall barge. And sometimes it looks like the water, if there was any splash, it would go right over the edge because they're so heavily loaded. How tall they look to be, it's not that they're different barges, it's just that the submergence depends on how heavily loaded they are. So the key item when it comes to buoyancy is the volume of water that's displaced and how much that water weighs. Ships, barges, submarines, any sort of a submerged object is displacing water. The water that would have been there if that object wasn't in its place. So here's an illustration showing some submerged object. And what this is showing is a distribution of pressures. Well, why are these pressure vectors bigger at the bottom than at the top? Because it's deeper. Farther submerged, right. So the deeper you are, the higher the pressure will be. So the pressure is bigger on the underside than it is on the top side of this irregularly shaped submerged object. Now it would be tough for us to calculate the pressure at a certain depth, because what depth would we use? Like, this is irregularly shaped. So what we can do, instead of looking at the difference in pressures from above and from beneath, instead, sometimes we can know the volume of that object. And one easy way to measure the volume of an irregularly shaped object is to have a full container, and then you dip that object into the full container, and however much water gets displaced, then you would use that Archimedes principle. You know how he got in the bathtub and the water level rose a certain amount equivalent to the volume of his body. So the same thing here is you can find the volume of that, and the external forces that are acting on the object are going to be the buoyant forces, the difference between the forces that are pushing up and the forces that are pushing down. So this equation that I'm showing is the forces that are pushing up are dependent on the volume of the object and the volume of the above the object. So those are the upward forces, but the downward forces are only dependent on the weight of the water that's above the object. And so the difference between the two is the buoyant force, the difference between what's pushing it up and what's pushing it down. And so it's a really simple formula. The buoyant force is the unit weight times the volume of the submerged object. Here we're calling this whatever the body is, object B. So anytime something is submerged, there's going to be a buoyant force. Ignoring surface tension, what determines whether something floats or whether it sinks? Its density, yeah. So if its density is less than the density of water, then it will float. If we want to think about it in terms of buoyant forces, if the buoyant forces are greater than the weight of the object, then it will float. If the buoyant forces are less, then it will sink. Okay, so let's just prove this to ourselves. Let's prove it to ourselves that a submerged object, its buoyant forces are dependent on either the volume displaced or the difference between the forces from above and the forces from beneath. When I say volume displaced, what that means is if, in this case, we've got a box, a 1 by 1 by 1 box. It's a cube, a plastic cube, and it's 1 cubic meter. If that plastic cube wasn't there, then the water would be there. You know, the water would fill in and occupy that space that the cube is right now occupying. And so the cube has pushed the water out of the way and has displaced it. So here, for step A, let's calculate the force on the bottom. So this F bottom, the way that we can find that, it's pretty easy since it's a horizontally oriented flat plate. All we need to do is pressure times area. So F bottom is going to be pressure times area. And the pressure that we have to consider is going to be at a depth of 4 meters because it's 3 meters from the water surface down to the top edge and then another 1 meter down to the bottom edge. So delta H times gamma times the area, and the delta H is 4 meters. In this case it's water, and so the gamma is just going to be our standard default value of 9810 newtons per meter cubed. And then the cross-sectional area, it's a 1 by 1 area on that bottom face. 1 meter squared. Okay, so the bottom force is the 39,240 newtons. And that's pushing upward. The force is going to be in the same direction as the pressure that's applied, and the pressure is acting perpendicular to the surface. And so if the surface is horizontal, then the force is vertical. So we've got an upward force of 39,240 newtons. Now B, what is the force on the top? It's going to be the same technique, but a different delta H. So it's delta H times gamma times A. So the delta H distance is 3 meters. The unit weight, 9810 newtons per meter cubed. And then the cross-sectional area is 1 square meter. Okay, so we can do that calculation and find that the downward force is 29,430 newtons. So that's pushing from above down on the cube. So the difference between the two, if we just subtract F bottom minus F top, it's going to be 39,240 newtons minus 29,430 newtons. So 9,810 newtons. And since it's positive, that means that the upward force from the bottom is greater. So it's up. The net force is up. Well, 9,810, that rings a bell. That's a number that kind of keeps coming back to us. So it's the unit weight of the water, and this had 1 by 1 by 1, so it was a cubic meter of water that was displaced. And so the buoyant force, the other way of looking at it, F sub B, is the unit weight times the volume displaced. And the unit weight is 9,810 newtons per meter cubed. The volume displaced is 1 cubic meter. So the buoyant force is going to be 9,810 newtons. So that kind of is a proof for us that, yes, this volume displaced approach is going to work. It's going to essentially be the difference between the forces from above and the forces from beneath. So sometimes you can calculate those directly like we just did, but if it's in a regularly shaped object, or if it's just difficult to calculate what is the depth to the centroid, then it's easier to use this volume displaced approach. Okay, so any questions about that illustration? Sometimes there will be an object that's only partially submerged, like that submarine was, for example. If it's part of it's below the water, part of it's above the water, the key thing that you need to keep in mind is it's only the submerged volume that contributes to the buoyant force. So in this case, although this object has some total volume, it's only the volume that's described by A, C, D, so that submerged component that's going to contribute to the buoyant force. Okay, to make that point of a submerged object that's only partly under the water, let's consider this example where we have a plastic block, and it's a big one. It's 5 meters tall, 10 meters wide, and 10 meters long. And it's floating in such a way that it's mostly submerged, but not all of the way submerged. So there are some things that we can determine based on how an object floats. Just on the way that the object floats, we can determine the specific weight and the specific gravity, ultimately. So what I'd like you to do is go through these steps 1 through 5, and based on this buoyant force equation, determine the buoyant force, the weight of the block, and this is in equilibrium. It floats in the water as shown. That means it's not continuing to rise. That what we're looking at is how it floats in steady state. So we're in equilibrium there. All right, let me pause this for just a moment, and you can begin your calculations. Density is a way of describing something, and we've been talking about liquids through this semester, but you can use density as a way of describing a solid as well. You know, like the density of a rock. There are some rocks that actually will float because they have a very low density, like volcanic rocks that have a lot of air entrained. So here in this example, I'm asking you to calculate the specific weight of the block and the specific gravity. And we usually think of those as being fluid properties, but they can be used to describe a solid as well. So the first step in all of that is, first of all, to consider the buoyant force. And remember, the key thing is it only depends on the volume that's displaced. And so that 0.4 meters of the block that's above the water line, that 0.4 meters that's above the water line isn't pushing any water out of the way. It's only the submerged volume of the block that's displacing water. So that's why we did 4.6 by 10 by 10, is that the buoyant force only depends on how much water was displaced by the submerged portion of the block. And then the weight of it is equal to the buoyant force because it's in equilibrium. And the volume of the block, we can get just that from the dimensions. And I'm asking this in a specific order so that you have the data you need to be able to calculate the specific gravity and the specific weight. So for this block, the specific gravity is 0.92, and I make the observation here at the bottom that that also happens to be the ratio of submergence. You know, if you look at 4.6 out of 5 is submerged, so that's not a coincidence. If the block was 50% submerged, then that would tell you that it has a specific gravity of 0.5. So you can use how something floats to estimate its physical properties. I'll give you a moment to finish copying that down if you still need to see it. There's an example in the book that takes this stuff to the next level, and we're going to step through that example because I think the book is good at explaining a lot of things, but sometimes it could use a little additional detail. And that example that we're going to do here in just a minute is one of those where a little bit of extra help would be useful. This one. What we have is a wooden block that's providing buoyancy because it has a relatively low density, that wooden block. And then there's a metal object that's also providing a little bit of buoyancy, but the metal object has a greater density than that of water. So if it wasn't connected by this cable, then the metal object would just sink to the bottom of the container. So this system together is in equilibrium. What's happening is that wooden block would probably be floating higher than it is if it wasn't attached by the cable to the metal piece. So the example in the book says to find the tension in the cable and the mass of that object number 2. So here's what we know. We're given the dimensions of the wooden block. We're shown that it has a height of 10 millimeters, and that of that 10, 2.5 is sticking out of the water surface. So that means that the non-submerged portion isn't contributing to buoyancy. And then it also has a 50 millimeter by 50 millimeter, so the width of it is 50 millimeters, and then into the page it has a 50 millimeter dimension as well. And the wooden block has a specific gravity of 0.3. And then the information that we have about this metal object is only its volume. We don't know anything other than that. But based on the way it's floating, we'll be able to calculate the mass of that object. So here's the steps I'd like you to follow. First of all, calculate the buoyant forces. And remember that the buoyant forces depend on the volume displaced. Now, these units are a little bit screwy. millimeters and cubic millimeters. My suggestion is to, from the very beginning, convert all of that into cubic meters and to lengths of meters. And we'll have some pretty small forces, but it'll just be easiest if you convert the units to the base units to begin with. So the buoyant forces on 1 and 2, and then the next step, you find the weight of object 1 based on the given specific gravity of 0.3 that they said and its volume. And then you can do a force balance on the object separately. And so the force balance for the block, if we just think about what forces are happening here. So it's floating. There's going to be the weight of the block, so we'll call that W sub 1. There's going to be a buoyant force pushing up. We'll call that F sub B 1. There's the tension in the cable pulling it down. Am I forgetting anything? No, I think those are the forces. If we do a force balance on 1. Now, if we do the force balance on object 2, that metal piece, there's going to be a tension pulling up. There's going to be a weight acting downward. We'll call that W2. And then there's going to be a buoyant force acting upward, F sub B2. The tension in the cable is going to be the same in the top force balance as it is in the bottom force balance. But starting with the wooden object, you can find the tension in the cable. And then once you know the tension in the cable from the top force balance, you'll apply that same known tension to the metal submerged piece and be able to determine what is the weight of it and therefore the mass. The key ideas that I want to save just a moment to show you because I think that'll help you with the homework. So let's just take a look at where this solution is heading. What we have to do first of all is calculate the buoyant force acting on both of those two objects based on their submerged volume. So that's showing on the screen right now, calculating FB1 and FB2. The weight of that object 1 can be determined directly since the specific gravity was defined. And once you have the specific gravity, then you can find a gamma for the block. And you multiply the gamma by the block by its volume. And now we know the weight of that first object 1. The force balance starts with the top one, the wooden block, to find the tension in the cable. And so the tension in the cable is just the buoyant force minus the weight. And once we know that tension in the cable, then it allows us to find the only unknown in the object 2 force balance. In the object 2 force balance, we know the buoyant force because we were given the volume. And now we know T because of the object above it. So the difference between the two, actually, combining those two forces together is where we get the weight. So we get the weight of object 2, and if we know its weight, then its mass is just going to be determined by dividing the weight by g. So that's the process that we go through, and you have a homework problem that's pretty similar. And so let me just spend our last 1 minute to give you the key ideas on this homework problem. It's a submerged like a submerged buoy. And they don't give you a picture in that problem, and I thought that maybe providing a graphic would help to clarify. First of all, it's submerged in salt water. And so you'll need to look up the unit weight for salt water, and it has that in the back of the book. The density and the unit weight's a little bit higher. So think about this anchor chain. What it's doing is it's pulling down on the buoy. And so when you do a force balance on this, the buoyant forces are going to be up, the weight is going to be down, and the tension in the cable is also going to be down. And they tell you what the maximum tension in the cable can be. And so what you're solving for is how much does the weight need to be in order to keep it in equilibrium. So the diameter of this sphere is given. So from that given diameter, you'll be able to know the volume and therefore the buoyant force. They tell you the weight of the buoy itself, that metal that's the outside shell. Then they also need to fill it with a certain amount of scrap iron to put it into that perfect equilibrium. So you're going to be solving for equilibrium where the tension in the cable is 4,500 newtons for that problem. One other key idea hint is I just thought the way that they phrased that problem was a little bit confusing. Basically, let's break it down this way. This block is sitting on a scale in air, and when it's in air, the scale is pushing up with the scale reading of 700 newtons. And that's what the scale says. That basically means the weight of it and the upward force are equal when it's in that measurement. But now when it's measuring that same block in water, then the scale is pushing up with 300 newtons. And so you can, from that difference, determine what the buoyant forces are. And if you know the buoyant forces, then that can tell you things like the submerged volume. So if you need to reflect back on both of these hints, of course, they're going to be in the video that's posted on YouTube. But I thought both of those could deserve a picture, so I thought I'd provide it. All right, that's all for today. I kept you 2 minutes, so I'll have to be sure to make that up to you soon. Keep in mind that we have an exam on Thursday, so we'll continue talking about some of these Chapter 3 ideas on Tuesday. Have a good one.